So, good morning. Good morning to all of you, to all our viewers, and to all the people who are watching the channel right now. So, this time we are going to answer the board exam, or some of the board exams, but actually part of the midterm exams given under HVAC-R, which is heating, ventilating, and air conditioning. So it was posted like 2 days ago, like it was in October 30. And most of the viewers requested that why don't we give the solution. So we are going to do that. We are going to satisfy our viewers. We are going to provide solutions for the uh, exam so that it will help our teachers and all the students who are following our channel. So this is the midterm exam in HVAC-R, and it was given in October 30. As we know, we have four problems. There are four problems in that midterm exam. One is about the cooling tower, and number two is about the rotary dryer, rotary drying of sand, and yeah, and number three has to do with the air conditioning, I guess, the air conditioning. And number four has to do with ice refrigeration. So ice refrigeration. So to cut the excitement, we are going to start immediately. So the first problem has to do with the cooling tower. It says the cooling tower of the 3 Mile Island, or the NPP, nuclear power plant in the 3 Mile Island in Pennsylvania, has an inlet temperature of 38 degrees centigrade. The wet bulb temperature of entering air from the outside is 28 degrees centigrade, and the approach is 4 degrees centigrade. So those were the only given. And what is being asked, what is being sought are the following. What is the theoretical range? What is the temperature of water leaving? What is the actual range? What is the cooling tower efficiency? And what is the shape or structure of the cooling tower based on hyperbola conic form that allows the rapid flow of hot air going upward the portion of the tower. So first we have to jot down the given, and we will be using this blank page. So here 28 degrees centigrade, then 38 degrees centigrade, right? So we are going to do that. Okay. Yeah, so here we have a blank page here. First, um, let me draw the blank page here. Let me draw the cooling tower. So we have the cooling tower. Let me change the. So we have the cooling tower here, yeah, and it is natural draft cooling tower because there is no fan, so the air is naturally uh, flowing from bottom up to the top. No, the air enters here from the bottom up to the top. This the exit of the air, and it comes in contact with the water, yeah, coming from the from the plant. There's a hot water, yeah. So there's a hot water here, yeah, hot water. So in this hot water, there's the T1, yeah, T1. the water entering, and here is the water leaving. Yeah, so this is the T2. But of course, there's a makeup water here because of the evaporation. We need to refill. We have to replenish the basin. Now, so somewhere here is the basin. In this case, the basin. But it says the the wet bulb here. So that there's a wet bulb here. Temperature. Yeah. And another thing, the approach was given, like how much is that approach in terms of temperature. 4 degrees centigrade. Yeah, 4 degrees centigrade. Okay, so now what is being asked is the following. Yeah, the theoretical range. Now, so theoretical range, the theoretical range is the longest range. Now, so the longest range um, would be T1 minus um, WB1. Let me check. No, T1, right? T1 minus WB1. So this is this, right? So T1 minus the WB1 is the theoretical range. So T1 minus WB1, temperature of water leaving, the temperature of water leaving, once you know the water leaving, it is in T2, right? What is the actual range? So actual range is T1 minus T2, the actual, yeah? So this is the actual, this is the theoretical, and when you divide the two, it will give you the cooling tower efficiency. So this one, no, cooling tower efficiency. So eta, eta is what? Theoretical, theo range over the actual range, now actual range. But the problem, I guess, is we don't have the temperature of the water living. Yeah, so T2, we don't have T2, but we have the approach, right? So the approach is another term. Now, so what is approach? So the approach here, if you remember the formula, is um, this T2, right, minus WB1, right? So um, WB1 now, which is here now, the wet bulb of entering air is 28, right? So 28, and you were given the approach, then you will get the T2. Okay, so we are complete with the data, so that we will be able to solve this. So here, let me give you a brief background of 3 Mile Island. So 3 Mile Island is actually a place, an island in the Pennsylvania, where this nuclear power plant was located. It was called 3 Mile Island because literally it is having a measurement or a distance of 3 mile. So 1 mile is 1.609 kilometers. So 3 mile from the river. So there's a river there, and that if you are going to measure three mile, then you will find this place. Now it is situated in this um, structure. So where's the cooling tower? So here we have two cooling towers. So this is CT1, cooling tower 1, and this is CT2. So this nuclear power plant is being subdivided into two. No, so one owner is operating the other one, and one owner is mm, operating the other. So, but in there was this accident, and this cooling tower two and the nuclear power attached with the cooling tower is no longer uh, being used. No, so but cooling tower one is used, and but last year it was shut down because of economic uh, instability, meaning that the high cost to maintain the cooling tower is so high that it cannot offset yeah the profit. Yeah, so they are not profitable. So unless the government will subsidize, but it was unfortunately it was shut down already. But what we are after is here, right? So the principle of cooling tower in this case is a natural draft, meaning there is no fan, no natural draft, no fan or no ventilation, no mechanical fan. If there's a fan, that would be called mechanical draft. This natural draft, meaning the air is naturally going uh, up because of this um, portion or this structure, which is called hyperboloid. Yeah, so hyperboloid. So you can see here, this is hyper uh, boloid. No? So this nuclear plant has 400, like 400 feet, no? 400 or 400 meters uh, in height, and the 850 megawatts supposed to be, it is going to give enough power to that place, yeah, in Pennsylvania. So here, so water comes in. So it is T1. Where is this water coming from? From the plant, for example, from the power plant. So uh, it is used to cool the reactor and other things now. So there are water jacket holes there, and other tubing stuff. So this red the color is hot water. So the hot water will come, and then it will be kind of uh, drizzle. No? So there's kind of a shower here, no? Like a nozzle that will uh, tend to drip the water. So here, due to height, there's a height, and then the water, hot water will come, and then here the air the air can enter. So here, look at this. Yeah, so there's a opening here, there's a air here. Yeah? So air can enter here. Then that air can meet this. So they will have contact. No? So this is a kind of wet wet type cooling tower, wherein the air will come in contact with the hot shower or hot drizzle, hot droplets. No? So of course, in there's a structure here now with a fill. Now, so there's kind of honeycomb structure like this. Yeah, it was engineered uh, structure so that the heat transfer should be uh, efficient. So here, the blue, this one will go back to to the plant. Huh? So going back to the plant. So here, there's another portion here. This is the makeup water. Yeah. So because the evaporation due to the evaporation of the water in the basin, it will be becoming less and less, yeah, due to the heat transfer. So the water will become less, so it needs some makeup water. But the logic behind this structure is this, like like uh Venturi. I don't know if you know the Venturi. Yeah. So there's a portion here. There's a portion here now. So it's like I just put this in a horizontal manner. So here there's a difference in the diameter. So here, if you have 3 points, 1, 2, 3, at this like a neck, yeah, like a neck. You see the area here is less, no? So the area, the cross-sectional area here is less. So when the area is less, what happens to the flow? What happens to the velocity? So by Bernoulli's theorem, yeah? So if the flow is area times velocity, so there's a inverse relation between area and velocity. So as the velocity increases, the area is less. Yeah. So if the area is less, the velocity of the air is high. So that's why it is like this, right? And then until it goes to the top, because the hot air, yeah, because when the air absorbs the heat from the water, it becomes hot. So when the air is hot, it becomes less dense. The density is becoming less, and in the gas theory, if the gas is less dense, no, or less weight, less density, it will tend to go up. So the less dense air will tend to go up. That's why it will come out rapidly like this, right? So here, if you are going to deduct T1 minus T2, T1 minus T2, you will get the um, actual range. But this one, T1 minus WB1, because there is a wet bulb here. No, there's a wet bulb in the mass of here air here. So T1 minus WB1 is the theoretical range because it has a longer range. Now, I mean, the difference would be more, right? But here, T2, there's a T2 and WV1. So T2 and the WV1, so that will make this term here approach, right? So let me flash the background for the theory. So here the theoretical range is the longest one. Yeah? So T1, look at this. So T1, this one T1 minus WB1 is a theoretical range, right? So the actual range is T1 minus T2, right? So T1 minus T2 is the actual range. And then T2, which is here, minus WB1, which is here. Now, this one, T2 minus WB1, is the so-called approach. So we were given the approach. I think approach, this is a like 4. And then W1 we have is 28, right? So 28. So if we're going to get the T2, so T2, meaning the leaving, the temperature of the water leaving is what? T2 equals approach plus WB1. So we have WB1 like 28, then plus 4. So we will have like a 32 for the theoretical range, right? So 32 for the theoretical range. So let me have this, right? So here is this. Now, what I'm saying is this, right? So approach temperature is the exit water, which is T2, minus the wet bulb temperature, right? So this is the wet bulb, this is the T2, okay? So that's gonna be the approach. So if you were going to get the exit water exiting the cooling tower, so 4 plus 28, you should just have to transfer this in another part of the equation. So it's going to be 32, 32 degrees centigrade. So this one is this, right? So 32 is the T2. Yeah, okay. So 32 degrees centigrade. So now we go to the first question so that we will be more organized. What is the theoretical range? So the theoretical range is T1 minus WB1. Do we have T1? Yeah, so we have a theoretical range. We have T1. So T1 is 38. No, it was given there, 38. According to the problem, the temperature of the water entering is 31, right? And 38 degrees centigrade, the water inlet. So 31, right? So 31, this one is 31. 38, 38 degrees centigrade. Then minus uh, 28, minus 28 is the theoretical range. So we have a 10 degrees centigrade. Now, the approach, we already solved this. So the approach temperature is the temperature of the water leaving or discharge exiting the cooling tower minus the wet bulb. So the wet bulb is 28, and then here there's a 4 degrees centigrade given for the approach. So what we need to have is T exit, which is T2. So we just have to transfer there. So 32 degrees centigrade is the answer for the T2. So let me recap. Yeah. So T1 is the hot water is 38 degrees centigrade. Then T2 leaving the cooling water is 32 degree centigrade. Now the actual range here. Now the actual range is the T inlet, which is T1, minus the exiting, which is T2. So we have 38 minus 32. So we have 6 degrees centigrade. This one. Yeah. So the actual is 6, right? So efficiency is range actual. What is the actual? 10. And then range theoretical, which is, sorry, range actual is, this is theoretical is 10, range actual is 6, right? So 6. So 6 over 10 times 100, yeah, is zero point 0.6 times 100. So the efficiency is 60%. So there's a efficiency of 60% in that cooling tower. So we go now to the number 2. The rotary dryer fired with bunker oil of 10,000 kilocal per kilogram higher heating value is to produce 20 metric tons per hour of dried sand with 0.5 bomb moisture from wet feed containing 7% moisture. So there's a wet feed containing 7, but the product is already zero point 0.5. Specific heat of sand is 0.21 BTU per pound per degree Fahrenheit. We could compute that because all the rest are in metric. So BTU per degree Fahrenheit, we could compute that as the specific heat of sand. Temperature of wet feed is 30 degrees centigrade and temperature of dried product is 115. So first it's 30, then once it goes out to the as a product that is dried, it is already 115 degrees centigrade. The specific gravity of bunker oil is zero point 0.9 and the dryer efficiency is 60%. Calculate the following in kilojoule per hour. So what are those problems? So the problem is this. What is this? Yeah, heat required to evaporate the moisture. Then heat absorbed by moisture that remained in the sand, and this one heat absorbed by sand from 30 to 115 degrees centigrade, because there are portions of the moisture that is being left after the drying. So that portion of the moisture will still absorb some of the heat. So in order to solve this problem, we have to at least give some kind of graphic illustration here, right? So this the illustration for this. There's a rotary dryer, and in all cases, it is being inclined. No? So it is inclined at some degree. So here is the feed. So here is the feed. So here is the feed. Look at this. What are the properties of the feed? So when it enters here at the feed, there's a 30 degrees centigrade and then 7% moisture, which is like zero point 0.07 0.07 in decimal. Yeah, so that's a moisture, then there's a wet feed. So if that is the feed as a F, so this is the product, right? So when it goes out here, this already product. So the product is 20, what is this? Yeah, 20. The output is 20 metric tons per hour, which is 20,000, right? 20,000 kilogram per hour, because it's in metric. And then from 7, it becomes zero point 0.5. No? So 7%, then it becomes 0.5%. And what are these percent? So this is percent moisture of the feed, and this one is percent moisture of the product. Yeah, so we will be using that later. So the temperature of the sand is 115. So from 30, look at this, from 30, so 30 in the feed side, it becomes high, no? 115. Okay, so definitely there's a heat transfer there. So the sand is 0.21 BTU per pound mass degree Fahrenheit. Let me have this. The sand is 0.21 BTU per pound per degree Fahrenheit. So if you are going to convert that according to Wikipedia or Google, it is 881 joule. Look at this, 881 joule per kilogram Kelvin. Okay, so those are the things. Now in order to solve this, you have to find the different parameters, like uh, the enthalpies. It's very important to find the enthalpies like this. Yeah, so where can you find the enthalpies? From the steam table, because it has this portion of water, no? So water, so that's why steam table. Yeah, so we should get the enthalpy of fluid na saturated, enthalpy of fluid at 30 degrees centigrade. Okay, so where's that? So this is the saturation temperature, and it says 30. Yeah, so 30 here. So 30 here. So here the 125.8. Now if you are going to have this, that's how it's this one, right? 125.8. What we have, this is 125.7, 125.8 kilojoule per kilogram. So here is this. Then we also have to see the temperature or the enthalpy of gas at 100 degrees centigrade, because the enthalpy is needed. Yeah, because if you multiply that with mass, you can have this heat energy. Now so here at 100 degrees centigrade, it says here 2676. Now from my old notes, so water evaporates at 100, so you go to 100. So there are different kind of tables, and sometimes they are giving different values. So look at this, at 100 degrees centigrade saturation temperature, the enthalpy of fluid, which is here now, these are the LHF, it is 2675.84 or 2676. Now, so later we will see if that is the the value of enthalpy being uh, found by the students. So another enthalpy that we have to know is the HF, again at 115 degrees centigrade. So here the table that I got from the internet has no 115, so it's just 114 and 116. So all we have to do is to interpolate. Yeah, so the method is interpolate. So if you are going to interpolate that, the data or the enthalpy of fluid should fall between 478. Yeah, so between 478.038 and 486. So I did the mathematics, and I found out that this is the result. Yeah, so this in between is 482.28 or zero point 0.3, but the others maybe 482.4 and so on. So we will see that. So after we get that values, we can now proceed. No? So first, here, the equation for the heat required to evaporate the moisture is this. Now, so meaning to evaporate the moisture, you have 30, this one, yeah, so 30 degrees centigrade fluid. No, so that is uh, I'm sorry, 30 degrees centigrade. Yeah, so you have a fluid there because it's water, right? There's a water 30 degrees centigrade kind of ambient temperature. Then this 30 degrees centigrade will become saturated at 100. So from 30 it becomes 100 due to drying. So why 100? Because from fluid it becomes a vapor. That's why there's a saturation point. The saturation boiling point of water is 100 degrees centigrade. So if you're gonna take a look at this, now comparing to the data that we have found, no, so here is 125.79, while here it's I think 126. Oh, 125, also 125.8. No, so here look at this, 125.8, 125.8. The other is 125.79. So only zero point zero 0.01. There's not so much of a problem. It's more of the solution that I'm going to I'm focusing on. No? So here 125.79, then enthalpy of fluid at 100 degrees centigrade 2676. So 2676, what we have in our uh, table is this, yeah, 2676, but this one is 2675.8. No? So kind of zero point zero 0.02, yeah, so 2676, 2675.84. Okay, so that is the value, and the last is this. Yeah, so what is the saturated I mean the enthalpy of the fluid at saturation point of 115. So 115 is here now, so 482.3 or zero point 0.4. Yeah, so 482. Let us see the solution here. What is the enthalpy of fluid at 115? We shall see later, right, at this one. So 482.48, while we have 482.3. Yeah, like that. Yeah, so it's zero point zero 0.01. Yeah, so now my point here is there are three heat that we are talking about here now. So heat required to evaporate the moisture. when we s- uh, when we talk about evaporation, we are evaporating from 30, yeah, then it becomes 100 degrees centigrade. So it becomes hot, it becomes dry. So definitely there's a portion that was removed, and that is the mass of or weight of water removed. Yeah. So here, what we have to do, because we need to get the mass. This one, yeah, we need to get the mass because this one we can get from the table, and this one we have the data from the table. So we don't have M. Yeah, we don't have M, but here we have this Q. No, because we can we can compute that later once we compute for the mass flow of the extracted water. So the formula is this, right? So bone dry mass of product equals bone dry mass of the feed. Yeah. So the mass evaporated is this, yeah, feed minus product. So feed minus product, so they are both in kilogram per hour, kilogram per hour. So feed has more moisture or water content. Yeah. So here is the principal bone dry mass of the product equals bone dry mass of the feed. So meaning the mass minus 1 minus percent MP, meaning the percentage moisture of the product equals F, which is the mass flow, is 1 minus percent MF, meaning you have to deduct from 100%. Now in decimal, one is 100%, right? So 1 minus percent MF, because you are going to we are going to put this in decimal later on. Yeah. So after you deduct the percent moisture, it will become dry. So 1 minus the moisture content, it is dry. So meaning dried product equals dried feed. Yeah. So here, substituting values, the product that we are talking about is this at 20 metric tons. So if you are keen enough, now you can find where that came from. So it is said here 20 metric ton. So here 20 metric ton per hour of dried sand, no, with 0.5% moisture from wet feed. We are being fed with the 20 metric ton. Okay, so here in the calculation here, so 20,000 kilogram per hour, which is 20 metric ton. 1 minus 0.005, because it is zero point 0.5, right? In the product, it's all zero point 0.5. So if you convert this into decimal, it's like this, equals feed. So feed is mass flow, which is kilogram per hour, then 100% minus zero point zero 0.07, because in the feed it's only 7%. If you're going to convert that into decimal, so we have 1 2, yeah, so 0.00, uh, sorry, 1 2 0.07, only 0.07 is correct. So 0.07, if you are going to manipulate the equation, it will become like this. So feed equals 21,397.84946 kilogram per hour. So if you have this feed, then you have the product, which is 20,000, right? So F minus P, no, that is the amount of mass that is being removed, no, or water removed, no, water removed or water extracted. Okay, so you just have to deduct. Yeah, so feed this one 21,397. This one is feed minus product 20,000. So you will get this, right? So this 1,307,84946. So if you have that, which is the mass, then you can substitute this, right? So this equation here, right? So you have the mass, then you have the H now at 100. So this is the I guess this the the enthalpy that we get a while ago. So 2676 na minus 125.79 26, right? 2676 here, yeah, or 75 set 2676 because it is rounded off. Then the other one is this 125, right? Because this is yeah 125, right? So if you are going to multiply that the mass minus H, no? H at 100, that is gas, and HF at 30, that is fluid. So you will end up in this 3,564,949.462. So what I'm calculating what is the the heat now. So this is this 3,564 949.462 because you can convert that in kilowatt now because kilowatt is just kilojoule per second. So but this one is we have this value, which is the 3,564,949.62. That is the value of Q1, meaning heat required to evaporate the moisture. So we go now to the number what? Number two. Okay. And number three. No, will continue that now because this the heat that's the only uh, problem we were able to solve. But there's another heat absorbed by the moisture that remain in the sand. There's also an heat absorbed by the sun from 30 to 115 degrees centigrade. So we'll continue tomorrow because it's too late, right?